4-3 kids, complements and conditional probability. And good news, we will not be doing Bayes' theorem, which is a little complex, and there is this Bayesian statistics that you could look into, and I think I'll probably be looking at it over the summer. But fortunately, I was told we don't need to cover it. So we'll only be covering this idea of the multiplication rule to several trials. So we're extending this, and then one probability that depends on another probability that already occurred. All right. Reminders of some things that we've talked about. If A is getting at least one event, almost forgot what that word was, then A prime is the probability of getting none of the events. Not A prime, sorry, A complement, A bar, no occurrence. So P, A bar, is the probability that A does not occur. And one way that we can then find the probability of A is if you find all of it, which is 100% minus that none occur, then you get at least one. All right? So it's a sneaky backdoor technique for at least one. All right. Accidental iPad damage is our first example. Square Trade offers you insurance on damage to different electronic devices that you purchase online. They find that 6% of iPads get damaged in the backpack. And so if we have 20 iPads, say we've purchased them for our work or school or whatever, and you're loaning them out, what is the probability that you get at least one that is damaged? All right. A, at least one of the 20 with damage. A bar, okay, the complement of A. It's all 20 with undamage. So the probability of A bar is, again, we take the complement, 1 minus 0.06, and then we have to multiply that times however many iPads. And that gives us 0.290. So about 29% of the chance that all 20 of them. So will be undamaged. And so 1 minus 0.29 gives us the answer, about 71% chance that one of them will sustain some sort of damage. Okay? Is it obvious why we don't take 6%? Oops, it's not even 6%, is it? 0.6 to the 20th power. First of all, this is the probability that all 20 of them will be damaged, right? And that isn't what we're after in this problem. It doesn't really help us. Okay? All right, conditional probability. So item number 2, it's going to be a short video today. Find the probability based on the fact that some other probability has already occurred. And the way you write that out is P bar A. Probability of B given that A has occurred. How do you calculate that? This is kind of the formula. I don't like actually to think about the formula so much as actually to look at the problem in terms of the chart, if that might make sense. So here's an example. What is the probability that somebody has a positive test result given that the subject uses drugs? All right? So we are given this piece has already occurred, right? Therefore, I am going to look at a particular row or column in my table. And in this case, the subject uses drugs I am looking at this column, or this row, right? And I'm looking at this as compared to that. Now, according to the formula, what is the probability of A and B? Well, the probability of A and B is 45 out of, again, the total is 550 and 55, 555. What is the probability now of just A? Like, right? That would be the probability of A. So 45 plus 5 is 50 out of 55. And so simplifying that, we get 45 out of 50. And reducing that down, we get 9/10. All right? So basically a 90% chance that somebody is going to get busted using drugs. Okay? Now, I don't necessarily like to think of it that way. I like to get my totals. So this is 50, right? And this is, for example, 65. And this is 485. And this is 505. Okay? And so I'm always looking at a row or a column. In this case here, I'm looking at the row of those people who use drugs. And so I would say 45 out of total 50. All right? To me, it's you can do it just as well as long as you've got a table. Yeah? Now, we're going to change this around and flip it around and say what is the probability that somebody is using drugs given that they tested positive. Right? So now we're looking at this column, as it were. So again, let me delete this, and so we look at this and we say, okay, it's 45 out of 65. Sorry, where did I get 65 from? 70. Okay? Again, I could do the probability of A and B divided by the probability of this, which is what I did over here. But notice it's going to always simplify down to that. And then that will reduce down to, I think, 9 and 14. I think, 9/14. So here we clearly see that if we turn around our letters or events, right? We don't get the same thing. Okay? These don't mean the same thing, and that's why. All right? Well, that's it. I was going to go through an example on Bayes' theorem, but I'm not. I'm going to include it for those of you who are gluttons for punishment. And yeah, you don't need to worry about that. And I'll make sure I go through and remove those problems as well. I think there's a couple of Bayesian problems in the homework. All right.